Um, so I'm sure everyone's aware that most composite processes can be broken down into three main steps. The first one is depositing fibers, whether they be dry or wet, consolidating the layers together, and then curing the polymer and or solidifying a thermoplastic. And these have historically been kept as discrete segments. Makes us ask some questions. Why have they been discrete all the way through history? Is it because of the size of the components that were originally made by hand layup? And as we get into bigger and more automation being used, would merging them together bring some sort of positive benefit? So we like to think that there's three main benefits to using layer by layer curing. Removing debulking, no exotherms in thick components. And also, it would be great if we could just get away from the bottleneck that is the autoclave. And there's definitely a few other positive aspects as well, including limiting out time of pre-preg materials and possibly introducing online inspection. Now, this sounds really great, but there's definitely a couple of really big research questions around interfaces, consolidation, and dimensional stability of the components that we might want to make. So to take a look at these three important aspects, I've got an example on the right-hand side of the screen. We can see a partially cured substrate with a couple of uncured strips being applied. So the first question is, will the uncured layers stick to the partially cured substrate? When we try to apply layer by layer curing, will the laminate that we've made in the end have the desired fiber volume fraction and low porosity that could allow us to replace autoclave type processing? And then finally, around the concept of residual stresses, is it going to create a warpage that's undesirable? So you might imagine that if you've got your first ply oriented at the 0-degree direction, and then it's partially cured, and you put a 90-degree ply on top of that and cure it, once you release the pressure, are we going to end up with a saddle, or are we going to end up with residual stresses that are so severe that we can't continue the process? So I'm going to walk you through a case study that I'm hoping will identify some of the issues that we're going to try to tackle, and show you that we have some information along the way that's going to take this technology a little bit further. So if we're trying to make a thick composite laminate, conventional curing tends to lead to a very high exotherm. So if you think about a single dwell process for a thick laminate, you tend to have a really significant overshoot in temperature just due to the curing of the polymer and the low thermal conductivity of the matrix. And one of the common ways to alleviate this problem is to increase the length of the process cycle. And you can either add multiple dwells, slow the ramp rates down. There's even the possibility of a thermal cooling. So all of these things then tend to increase the time. So what we need to be able to do, or what we're hoping to be able to do, is to intensify the process and save time as well. So the way we looked at that with layer by layer curing is we started by creating a digital twin of our process. We broke the laminate down into a series of sublaminates, where the first layer would see the pressure and temperature of the entire process, but the final layer, so layer N, would only see one temperature and pressure cycle. And if we run our digital twin, where we've coupled the consolidation and the curing together, we can see that it's always going to be more effective for thick laminates to approach this problem with a sublaminate type solution. So if we look on the right-hand side, we can see cure time as a function of temperature overshoot. And this is for a target cure of 120 degrees centigrade. So within our conventional process, we can run a series of solutions, and the minimum tends to become the Pareto front. And by examining the layer by layer process run at a couple of different boundary conditions, so the gray X will show you how, if we wanted to process the component in an hour, we could do that, but we'd have a 50 degree centigrade overshoot. processing the component in 2 hours, not as severe an overshoot, but 15 degrees centigrade. And potentially, we have the ability to take advantage of that to achieve our target process temperature. So when we actually manufactured a 300 millimeter by 300 ply laminate. It was 100 millimeters by 100 millimeters, so I have it here. Proof it really does exist. There's also a photograph in the on the slide. And we were really quite impressed. The volume fraction was fairly good. This was processed at 1 bar. Yes, it was a flat plate. We processed it in a test machine where the platens were kept at a constant temperature. So this gave us really good control of the thickness that we were trying to achieve and the pressure. Now, if you look at the temperature versus time plot in the center of the graph, you can see how that first sublaminate experiences the cyclic temperature through the process. And as we add sublaminates, they'll have fewer consolidation and temperature cycles, but they tend to have that 15 degree centigrade temperature overshoot. And if our target process temperature is 120, we're actually within about 5 degrees centigrade. So marrying up the traditional manufacturing targets. And I'll remind you that this process took a little over 2 hours, but it was still a good 30 or 40 minutes faster than a conventional process. I'll just note that there was no debulking applied whatsoever in this instance. So we just laid up the laminates, chucked them into the press, squeezed it at elevated temperature, and the results that you see are the results that we obtained. And through testing of what happens in the interfaces, what we were able to identify was that if we are able to keep the degree of precure of the sublaminate to gelation or a little bit lower than gelation, we can preserve the interlaminar properties measured by double cantilever beam testing in blue or interlaminar shear testing in black. And examining the microstructure using an optical micrograph, we can see that we've got fairly even thickness between plies, but there are some darker areas that look a little bit suspicious. Now, initially we thought these were voids, but by zooming in a little bit closer using an SEM, we were actually able to identify that it's the microstructure of an additive that was introduced into this material. And the same microstructure is visible in an equivalent autoclave cured laminate, but the sizes are a little bit different. So with layer by layer, we have intensified the process. We need to keep an eye on whether or not we're actually changing the microstructure of the composite and whether those properties are equivalent to a baseline. But overall, the quality looks really good. The porosity is fairly low, and the interlaminar properties are there. So to summarize, we're trying to bring deposition, consolidation, and curing into a single manufacturing process. We're looking to eliminate debulking and exotherms and the autoclave. We've proven that it's possible on a fairly small but very thick flat laminate. And we're just starting the journey now to take this into the automated space. We've got some great project partners, including large companies, small, medium-sized businesses, another university, and the National Composite Center, part of the High Value Manufacturing Catapult. EPSRC is supporting some of the work at Cranfield and Bristol through the SimComp grants. We've got in-kind PhD and NGD researchers, and we're expecting a good interaction with our industrial partners. So we've managed to have a kickoff meeting during lockdown, and there's a very strong excitement around this activity. We're in the process of designing rigs that are going to allow us to do continuous processing in an automated fashion. So at Bristol, we're going to focus on automated fiber placement, and at Cranfield, the activity is going to be centered around filament winding, possibly some pultrusion maybe even a combination of the two. So we need to look at some new materials. We've got some existing materials in the toolkit aligned to the specific project partners, and we are beginning our journey. Well, we've just started the journey, and we'll be taking that through to the next about 3 years. So with that, I'd like to thank you for your attention. If you have any questions, feel free to ask them now, or feel free to get in touch with either Alex or myself at any point in the next 2.5 to 3 years.